Hi guys. Sorry, I'm not Kenny, but unfortunately Kenny is not here today. So yeah, fool me all you want. So, welcome to RITSEC week 12. Clap it up. Come on, guys. I know you're tired. Sorry, we're almost there. We're almost through the semester. All right, let's run through some announcements real quick. As y'all know, join the Discord. If you're not in the Discord, you can't sign in. Can't basically do anything. Anyone need this? No? Cool. Got it. All right, please sign in. Sarah, can you turn on the sign in? Thank you. Everyone, I think, is well aware of how to sign in by now, but if you don't know, you can go to the sign-ins category in Discord. There's a general meeting channel. You just react to the message as soon as Sarah spawns a sign in. Just react to the message, and that's how you sign in. If you don't sign in, you're not an official member. You need to sign into 3 separate events. Thank you. Check the calendar. This is where we post all our events. So if you don't know what we're doing when we're doing it, go to this link, calendar.ridsec.club, scan this QR code as well. In the bottom right-hand side, a lot of people don't know this. You can click this little plus and we'll add it to your own calendar. That way you don't have to keep going to calendar.ridsec.club. Join the mailing list if you want to receive the weekly newsletters and other miscellaneous emails from us. I promise we don't blow up your email as much as my courses. Mail.retsec.club. Wow, that one did not land. It's okay. I know you guys are tired. All right, so some announcements. Tenchi's not here to announce this, but Hack the Box University, the CTF is going on. Team Contagion will be competing. Tenchi asks that you fill out this form to sign up if you want to compete with them. I'll leave that up there for a second if y'all want to scan that. Otherwise, if you do miss this, you can also go in the Contagion channel and message Tenchi. Just everyone at him like a billion times. You should add him in now. All right, are you all good? You got it? Okay, cool. Moving on. I don't see Mav around here, but we are starting to build ISTS, okay? If you would like to help us build ISTS, you would like to sign up to be a part of the ISTS Black Team, please scan this QR code. I think an announcement went out about it yesterday. Fill out the form, sign up, come help us build ISTS. It's a real good time, and we need a lot of people because it's a very large competition. So, highly encourage it. Anyone need that link? All right, cool. All right, yes, there's a lot of text on here. That's because Albie asked me to read this verbatim at the general meeting. So tonight there is a board game night, okay? I don't remember exactly what time, to be honest, but it's going to be tonight. 8 p.m. All right, I forgot to put that on here. All right, so Albie said, come to the RETSEC board game night, Friday the 18th in the club room. There will be board games. There will be hot chocolate. There will not be any llamas because Kip forgot them again.
Where's Munson?
Oh, yeah, no. Oh, actually, so Munson is not coming, and in solidarity, Albie is not coming either. So, yeah, be there or be square, okay? Anthony, Mr. Anthony, sure. You can come up here and do it.
In all caps, slide roulette has just dropped an announcement to the sign-up form. The sign-up form is an announcement now. So what slide roulette is, say I make a wacky zany presentation on tongue twisters, and then Brad has to present that, and he has no idea what he's showing up for. He shows up, and then he finds out his presentation, like right at the moment, and it's like, okay, present. You make a presentation, somebody else presents it, you get somebody else's presentation. It's really wacky zany. It's a really fun time. And yeah, that'll be December 2nd, I believe, will be slide roulette. And presentations are due to me the Wednesday before, which is November 30th. So you can reach out to me with any other questions.
Oh, it's also not being streamed. Sorry, stream. But if you want to come to this, come in person. You got the next one too.
And because we want to make the blog more wowzers, I decided to kind of to get more motivation to post on the blog. Your first blog post is now worth a full point instead of the half a point that it was before. And then any subsequent blog post after that will be worth a half a point. And you can only get your lanyard if you do a presentation. So even if you get the point, you will be presented your lanyard after your first presentation. Yeah.
Cool. So cool. Thank you, Anthony. All right. So, a little bit of a update. I'm sure some of you have seen the Discord, but we are going to be saying goodbye to Jake after this semester. He's graduating, so he's decided to step down from the IRSEC CTFCA position. So we are holding a special election. Unfortunately, the only meeting we have left is slide roulette. So yes, we will have to keep a strict timeline on slide roulette because we're going to use up the first half of that meeting for elections. There's a nomination form in the Discord. No, I'm not going to put it on the stream. You have to be a member to nominate someone. Go fill out the form. It requires your name and the person you're nominating and their email, I believe. We'll collect nominations. This form will close next Friday. If you are nominated, I will reach out to you over the course of this week to accept your nomination. We will have everyone present on 12/2, the slide roulette day. Everyone will present. You guys will get a chance to vote. If you would like to vote, please make sure that you have signed in to 3 separate events. So go to your DMs with our bot. Make sure it says total sign-ins, at least 3. That will make sure, and that includes today and next meeting if you want. That makes sure that it'll allow you to vote. Otherwise, it will automatically decline your vote. So please show up, vote, as well as if you know people who want to run or you yourself want to run, you can nominate yourself for other people. All right, now for the fun part, clap it up for the sponsors. Let's go. Keep it going, keep it going, keep it going. Let's go. Yeah, no, we really appreciate all our sponsors. Literally none of this would exist without them. It takes a lot of money to get this stuff done, so we appreciate it. Follow our social media. Sophie's doing a fantastic job on our social medias. If you haven't been keeping track, our Instagram is kind of popping off right now. Twitter is doing all right. We're trying to get some more on there, but maybe questionable after this past week or two. We're not going to discuss that. All right, so without further ado, I'm going to hand it over to Jake to present reversing and binary exploitation. Clap it up for Jake.
So transition of how you want to take your laptop back.
Mm-hmm.
So I'm having Fedora desktop.
Do single.
Yeah.
Leaks.
Oh yeah. It's like you've already seen this. All right, where are we starting? There's so much.
From the title slide.
We're gonna do it again, boys. Oh no, didn't want that. I mean, actually,
You can just click present.
That also just works. We're having a bit of a skill issue right now.
No.
God. There we go. Wow.
All right, give it up for Jake.
Again. It's on. Now it's on. All right, let me get set up again. If I do this, does that work? You guys hear me? Yeah. Cool.
As long as the stream can you see the
Maybe? Yes. The bar's moving. We're good.
Okay.
I might just mess around and run for CTFCA as well. Just stay an extra semester.
Yeah.
Screw it.
also your Twitch guys on a product.
Oh, all right. For our 5 viewers, yes, let's go. Woohoo! All right. Reversing. Let's go. If anyone has come to my reversing meetings, you probably know how this is about to go. All right. Lots of quips, really bad jokes. We'll see what happens. All right. All right, cool. So let's start. What's reversing? Has anyone here already taken 202? No? Yeah, kind of? Yeah. So, this is going to be a review. I don't really like 202, but that's my own opinion. So, reversing, or RE, stands for reverse engineering, aka the art of figuring out how something works. Reversing typically refers to understanding how a program works, but it could refer to other things like you might get like a PCAP file and you might reverse how a protocol is working. But generally speaking, when I'm talking about reversing and other people, we're talking about binary reversing. So hopefully you all like assembly. I love this quote. All right, if you're good enough at reverse engineering, everything is open source. Olivia would be proud. Free and open source, everything. All right, so why should you care? So a lot of what we do is malware analysis, typically with reversing. If you want to go into some Adobe software, you could discover some trade secrets, make some lucrative, but please don't do that. We're all white hats here. Don't go selling trade secrets to secret, shady, black market deals. Another thing we do a lot is with reverse engineering, we do that to kind of find vulnerabilities. So not every piece of software that has vulnerabilities is open source. So you kind of need to go through and figure out why a program is not working the way it is. We also do something called binary patching. So again, if you don't necessarily have the source code, that doesn't mean you can't actually compile the program. So what you can do is you can go through and just kind of patch it and make it work again by writing assembly. Everyone loves assembly. And, generally speaking, reverse engineers are masochists. We don't do this because we like to. We'll do this because we like pain. All right, so where does one begin? So there's two kinds of analysis, typically speaking. You got static analysis and dynamic analysis. Static analysis typically revolves around like looking at the file and the binary data, so you're not necessarily running it. Generally, you'll start by looking at the strings in the file, looking at the file metadata, looking at header info, etc. Some useful tools, I said this already, strings, PEView, elfdump. We'll talk more about those later. Static analysis also happens whenever you disassemble the file. This is where the masochism comes in. Sometimes you can even decompile it. So if you're using something like Ghidra, you can actually decompile it to a high-level language like C. So you don't necessarily have to read assembly. And then sometimes you even have the source code or pseudo-source code. So for instance, JavaScript, sometimes malware authors will obfuscate their JavaScript, but it's very easy to de-obfuscate it because basically all they're doing is eval statements. And Java, the one nice thing about Java is it basically decompiles directly into source code. So if you have a jar file, you can turn that right back into source code. All of your classes might just be named letters, though. And then the fun one, dynamic analysis, this is when you actually run the program. And hopefully something happens. And hopefully you're not doing this on your computer. I personally just kind of run it on my computer because this is like a live VM. I don't care. I've installed an OS on this thing like 15 times in the last 3 months. But don't do it. Do as I say, not as I do. Create a VM or a sandbox to run all of your malware in. Unless you're real ballsy. All right, get into some terminology here. So I kind of talked about this earlier. So we have binary executables. So this is typically like files, like your exe files, or if you're on Linux, ELF files. And I think on Mac, I forget what they're called. I think they're mock files. It's weird. So this is like the file you execute, aka you double click on it and it runs. Another kind of terminology we talk about, so we have high-level languages, or HLLs. This is like your readable code, C, C++, Rust, Go. There's a bunch of other compiled languages. Typically, this refers to languages that are compiled, but it can sometimes refer to things like Java, Python, to an extent. Then we have assembly language, which is the human readable machine code. So your CPU reads all the zeros and ones. You read English. Hopefully you're not reading binary data. That's getting a little too much into the masochism. The one nice thing about assembly, though, is it's an almost one-to-one translation to machine code, meaning the operations that you write in assembly are almost exactly transpiled to binary data. And syntax is dependent on one CPU architecture you're doing. So there's x86, x86-64. That's like Intel-based assembly. You got MIPS assembly. You got ARM. I think there's a few other ones like PowerPC. I can go on. There's so many. ARM is what runs on Raspberry Pi. So if you guys ever want to disassemble any Raspberry Pi files, you're going to need to know ARM. And then finally, machine code, kind of talked about this earlier. This is, again, what the CPU reads, and most of the time it's just binary information, so your zeros and ones. All right, more terminology continued, because this is a very complicated topic, and I could talk all day about this. So kind of talked about this earlier. We got disassembly and disassemblers. This is the process of turning machine code into assembly language. We use applications like Idra, IDA Pro. There's another one called Radare that's completely command line based, but it's very powerful. I'd recommend trying out sometimes. We even have decompilation and decompilers, so this will translate machine code into high-level language. Typically it's C, sometimes C++. Apps like Ghidra have a decompiler built into it. IDA Pro, the non-free version, has a decompiler built into it. I'm not going to talk about ways to get IDA Pro for free. That's for someone else. Ask someone older and not me. There's also a program called Cutter, but this actually just uses the Ghidra plugin. Ghidra really changed the whole landscape whenever it came out in like 2019. They had to say just kind of dropped it. No one knew it was a thing, and then it happened, and then everyone was like, screw IDA, we're going to use Ghidra now. But people still use IDA because it's paid, I guess. And then finally, we got a debugger. This is the tool that you'll use to run a program, and then you can interact with the machine state. You can set breakpoints. You can examine the memory. You can even adjust register values while it's running. Some of the ones that we use, so on Windows, we use WinDebug, AllDebug. On Linux, we use GDB. There's PwnDebug. That's actually a wrapper around GDB. Oh, and then another one we use on Windows is x64 debug. I typically use x64 debug on Windows. I just like the UI better. AllDebug is what you use in like 202, but it's ancient, and I think the last update came out in like 2005. So, are they using x32? No, thank God. It's a very old program. Most of the things you can do in Ollie, you can do in x64. WinDebug's also kind of nice if you're doing anything at like the kernel level. If you want to debug any like driver stuff because it's built into the operating system. So if you ever want to play around with that, hit me up. All right. So let's start from the very top on how we actually get to machine code. So we start with a high-level language like C, and then that gets assembled into assembly language, and then that assembly gets compiled into machine code. So you kind of see this little pyramid we have here, where you start with the very top with C. Fortran and Pascal are very ancient languages. Don't worry about those. So those are like the high-level languages, and then on top of that, or below that's the assembly, and then below that's the machine language, and then finally, you have your hardware that runs it. All right, now the fun part. The part that you all were waiting for. Now you all love assembly. I know I do. Or you'll learn to love it. Trust me. It gets better eventually. So typically when we talk about assembly, it's not really doing much. All it's doing is moving data. It's either operating on data, or it's literally only moving data or operating on data. Those are the only two things you're really doing with assembly. So you're either moving stuff in and out of memory or between registers, or you're doing some arithmetic operation on that. And that is basically all your computer does. It's just a bunch of addition. You just have a glorified calculator in front of you. We're going to be real. The most basic way of storing data on your CPU is registers. It's also the fastest way of storing data. So on x86, we have about 8 general purpose registers. There's more when you're doing 64-bit stuff. But we're going to continue talking mostly about 32-bit for the most part, because it's just a little bit more simple. But most of the concepts that we talk about will translate to 64-bit pretty easily. So, as I was saying, here are the 8 general purpose registers. So you have EAX through EDX, ESI, EDI, and then when you're dealing with stack stuff, you have ESP and EBP. And one thing to keep in note is that EAX through EDX, they can actually be split up into individual components. So AX will reference only 2 bytes of the 4-byte register, and then AH and AL will represent 1 byte of the register. Those are useful for doing operations that only require small portions of the register and not the entire register, so you don't have to do like bit masking and stuff. Just a little fun fact. All right, so let's kind of talk about some of the operations I was talking about. So on x86, there are over 1,500 operations, and as of now, I think there's actually more than 1,503. Intel likes to just add operations because they can. Doesn't necessarily mean that they're good. You really are only going to use like 30 of them, but you have 1,500 to choose from. The most commonly used ones are the move operations. So that's kind of used to move data in and out of a register. Sometimes it's even used to move data in and out of memory. You also have the add operation. That's pretty self-explanatory. You're just adding stuff together. There's the sub operation. It's used to subtract data. Again, pretty self-explanatory. I think a lot of these are pretty self-explanatory. The mul one does multiplication. The div one does division. The fun one, though, is LEA. So that loads it's called load effective address. That's what that stands for. And it loads the address of something in memory to a register. So instead of loading the actual value that's stored in memory, it will load the address of that thing in memory. This is really useful for when you're doing like array stuff and you want to index into an array. You're going to have to do everything with memory. This is in my opinion, my favorite part of reverse engineering is understanding how memory works. So yeah, registers are cool, but you can't use registers for everything. Not everything you're going to be dealing with is only 4 bytes long. I know, I wish that was the case, but it's not. So we have, in most 32-bit applications, you essentially have access to 4 gigs of virtual memory. And we use memory to store most of your data, including the actual executable part of your binary, your stack and your heap. We'll talk about that more later. And this is kind of how it looks on your box. So starting from address 0 all the way up to address 0xFFFFFF, go on. This is kind of how the memory layout is. So on Windows systems, most of the time your program's loaded in at 0x08 04 8000, and that's kind of where you start execution. Text references the actual executable part of your program. Then you have the data section, which is where all of your data is stored. You also have what's called a BSS and a row data section. So BSS is kind of your global data. Think of like using the static keyword in like Java and even in C. Then you have the heap. That's kind of your dynamic memory. And the fun one, stack. We'll talk more about this when we get into binary exploitation as well. Stack's kind of what holds all of your local variables and stuff. And then finally, you also hold the kernel in your address space as well, but that's not really accessible to you as a process. So yeah, kind of started talking about the stack earlier. So the stack is really useful. It's a first in, first out, or first in, last out. I forget how that works. Sorry, it's been like 3 years since I took CS. But either way, it stores information like local variables, the return address, where the actual stack is pointing to right now. It's really useful for whenever you're writing a program because you don't always know how many variables you're going to need at compilation time. And a lot of the size of your data might be dynamic. It's useful to have something like a stack. Also, the nice thing about the stack, it also stores where all the parameters that were passed into the function. One thing to keep in mind is the stack, instead of growing up the address space, it actually grows down the address space. So in order to allocate more data on the stack, you actually subtract from it, which is kind of a weird thing to think about. Because typically, first intuition is, oh, I want to add data, I'm going to add to the stack. That's not the case. You can access the stack using 2 registers, so ESP and EBP. ESP stands for the stack pointer. That points to the top of the stack, but it's actually the bottom of the stack because, again, we're subtracting. It's weird. And then EBP is the base pointer, so that's kind of the bottom of the stack, but if you're thinking about it. So this is a great graphic. So EBP is pointing to the actual base pointer, and then as EBP goes down, aka you're allocating more space on the stack, ESP actually stores the end of the stack. So you can kind of get what your stack size is by taking ESP and EBP. The heap. This is where a lot of your problems will come from, especially if you took, I guess, 202 or 201. If anyone here took MOPS, I doubt. I don't think anyone does that anymore. Programs are very unpredictable. You don't always know how much memory you need. So that's why we have something called malloc. Allows you to allocate memory dynamically, so you can allocate however much you want within reason. Don't go allocating 40 terabytes of memory. You're not going to get that. It's going to fail. Oh, that's a typo. Whoops. So heap is memory, like I said, dynamically allocated. Look for these functions whenever you're disassembling because a lot of vulnerabilities come from people not freeing their memory. or allocating too much memory. Yeah, even though this is a meme, the amount of times that I've done this where I haven't necessarily freed all the memory, and then you wind up using up all of your system's memory because you just keep allocating more and more and more. It's a great way to slow down your PC. Not as cool as a fork bomb, though. I love fork bombs. All right, so we've been talking a lot about data, but it's kind of weird if you don't actually have any ability to do anything with that data. So in most programs, we have this idea of what's called control flow. So programs don't always have a direct control path. So if-else statements, right? If this, do this. For loops, you got to do something. For loops are literally just an if statement in disguise. We're going to be real. In order to branch, we have a couple conditional statements. So there's in assembly, we have a jump statement that basically allows you to jump to a new location in memory. And jumping will change the EIP register. So this is another very important register to keep track of. The EIP keeps track of the last address that was executed. Normally, EIP will only increase by one instruction because you're normally just going sequentially down the executable portion of your program. But whenever you're jumping, it will actually change to the jump location. So that way, you can kind of keep track of where your program is at any moment. This is how debuggers are actually able to kind of keep track of your program. They just look for changes in EIP, and then they just follow those changes whenever it's going on. So here's a little example. It's kind of a double-edged sword. You get to look at assembly, and I get to teach you about control flow. I'm a great teacher. So if we're looking on the left side, that's just a very simple main program. I initialize A to be equal to 9, and then I just do a little if statement. You know, if A is less than 11, return 0, else return 1. Typically, your compilers are very smart, and they won't actually generate this thing on the right. They'll notice that A will always be less than 11, and it will literally just always return 0. So I had to turn off optimizations to get this code, but that's neither here nor there. So we'll just kind of work programmatically down the down this side on the assembly. So can you guys see my mouse? Yes, you can. Can people on stream? Yes, they can. All right, well, that's great. All right, so the first thing we do is we actually have to set up the stack. So that's what these two instructions are doing. Basically, we are pushing the last base pointer onto the stack so that way we can keep track of it and reset it whenever we leave this function. Then we set both the base pointer and the stack pointer to be the exact same thing because right now we have 0 things stored on this function's stack. So this little instruction right here is actually putting some variable onto the stack. So for instance, since it's an integer that's only 4 bytes long, we're allocating 4 bytes on the stack, which that's what this is doing right here. We're subtracting from RBP. We're putting 9 into it, and now that's what A is represented in our assembly program. By the way, the thing I'm doing all this in, it's called Compiler Explorer. It's a really useful tool if you want to start learning assembly. You can like write your C on the left, and then you can see exactly what it compiles to on the right. And then it even actually shows you what parts of your C code are in assembly. So that's kind of like these colors match up with what's going on in the C code. It makes it really easy to understand what's going on. So next we're doing what's called a compare statement. So what this is going to do, it's going to do a logical AND with the information, and then it's going to set a flag. And then we can use this jump if greater command. So what this will do is if 9 is, I guess, less than 10, or no, if 9 is greater than 10, then it's going to jump to L2, which is setting, so EAX is the return value. So it's going to jump to this portion, it's going to set 1 into our return value and then return. But because 9 is not greater than 10, we're actually going to put 0 into our return value and then jump to the end of our function and then return. One thing that's weird, and that's kind of just some compiler stuff, instead of actually doing what we're doing here, where it's seeing if A is less than 11, it's seeing if A is greater than 10, which is a weird way to think about it, but typically compilers have like a preference for one jump statement over the other, and you'll never know why. Compilers do things in really weird ways, and there's no point in trying to understand it because that is a really, really messy thing to start going down a rabbit hole on. That takes like years of knowledge. I started trying to do it over the summer. I should not have. I just gave up. Don't do it. Learn from me. Don't do it.
There were some good resources put in Discord the other day.
If you want to get started, I recommend looking into LLVM, just because it's highly documented. But don't go to the GCC path. That's what I did. Don't do it. All right. So now we're going to talk about for loops. Just a little example here. Another, again, nice thing here. We have all of our memory or all of our stuff kind of highlighted, and I can show you exactly what's going on. We're doing a lot of the same stuff that we did in the other program. We're setting up the stack. Then we're setting A equal to 0, and then we have to allocate another variable on the stack, which that is going to be I. So that's what this code's doing. You can kind of see that right here. So lines 5 and 6 on the right side, lines 3 on the left. We actually have to allocate our variable I on the stack. And then, as I said before, for loops are really just if statements in disguise with a jump statement. It's kind of weird to think about it in assembly because what you're doing is you're just kind of going down and then you're jumping back to it, and then going down and then jumping back to it. I'm going to disregard lines 8 and 9. All this is doing is just adding I to EIX. That's what these two are doing. And then we're adding 1 to I. So again, this is highlighted in purple. So there's a lot of instructions that go into this one simple line in C. So that's the equivalent of I++. And then this is the fun part. The fun part that I actually want to talk about here is this compare statement. So again, we are comparing if I, which is RBP minus 8, we're comparing that to 14, and then we're jumping if it's less than or equal. So instead of doing less than 15, we're doing less than or equal. I don't know why. Again, compilers are weird. And after we do that comparison statement, we do that at the end of all the logic inside of the for loop, so that way we can jump up right back to the top and then do this over and over again. And then if this fails, then we just pass through, we move the A into the return variable, and we return. Now, I'm not expecting any of you guys to actually understand everything that I just spurted out at you. This is really just a bunch of basic examples. I'm just trying to spark your interest here. If I could explain assembly in 1 hour, or I guess like 30 minutes, I don't think anyone could do that at all. And if you guys actually understand and you never understood assembly before, you're goated.
Or to reverse it.
Yeah, come to my reversing group. I need someone to take over because, like I said, we're graduating. Big sad. Oh no, not ready for real world. All right, so we talked about reversing. Now let's go into why we reverse. A lot of why we reverse is we are looking for vulnerabilities so that we can exploit it and then make money off of it. Hopefully in a legal way. Hopefully, all right?
Bug bounties.
Yeah, bug bounties, definitely. Or you go work for the government and they tell you to go exploit something. Hypothetically. Hypothetically, of course. We would never do that. All right, so what is binary exploitation? This is pretty easy. You're basically exploiting flaws in a program. Software is not perfect. Programmers are not perfect. We write a lot of things that just work because we need it to work. I mean, let's look at half of your homework assignments. I can tell you right now that those things are not perfect. Typically, there's something that you've done that is unintended, and people like us, we like to exploit that fact. So we transition to a state that is unintended by the programmer. But how do you find these flaws and vulnerabilities? Well, that's the whole point of this talk. Just keep listening. So what we do is we like to look for something and do something that the programmer didn't consider. So, I mean, it could be as simple as a buffer overflow, but it could be as complex as we are editing config files that are loaded dynamically into the program, and then it causes it to run some function on another server. It can get quite complicated. But most of the time what we're doing with vulnerabilities is we're looking for a specific class of bugs within the program. Most of the time, if you do this long enough, you'll start seeing that a lot of programs have a lot of the same issues. So it gets less complicated the more you do it, but like all things, with practice, things get easier. So let's kind of go through the process of finding a vulnerability. So we start with looking for an interesting area of code. This could be something like messy logic. We like to look for things like switch statements with like 5,000 cases. Maybe it's a for loop, or maybe it's just a code that just looks wrong. Typically, if it looks wrong, it is wrong. Historically, lots of bugs. If there's like a lot of bugs in that area of code, if we're talking like open source software and we're finding a lot of CVEs in this one file, well, let's keep looking in that one file because historically there's already bugs there. And then we also look for important areas of code. So I don't know if you guys heard, I think it was like a year and a half ago now, they found an exploit in sudo that allowed you to just kind of do whatever you want. The way they found that was they first identified a program. I didn't even think about talking about that. Identifying a program to find exploits in is just as important as finding areas of code to actually find vulnerabilities in. We like to use programs that are very commonly used. I think almost every Linux utility has had some bug bounty on it at some point, just because everyone uses it and it's very important to the code base. But then whenever we get there, you start working your way around the program. You'll start in the main function and kind of work your way out, following the control flow that I was talking about earlier. Most of the time, we like to stick with things that are open source, but it's not always open source. That's why we have reversing engineers. Finally, or secondly, now we got to analyze the code. After we find something that looks weird, we actually have to understand what the code's doing is. Then we try creating results. And then we do stuff that just causes results that are unintended. A good starting point for finding a vulnerability is looking for things like integer overflows and underflows. So basically taking, like let's say we need to store 64 bits of data, but we're storing it in a 32-bit int. That's an integer overflow. Underflows kind of happen whenever you're dealing with signed integers. We're looking for things like array out of bound exceptions. This means that you have essentially extended past an array. Not good. Array out of bounds kind of lead to buffer overflows. Buffer overflows are basically when you have a buffer and then you put more data than that buffer can hold into that buffer, and then stuff happens on the stack that's not good. We're going to talk more about that later. And there's so many more. There's so many different vulnerability classes. I could spend like 50 slides on all the vulnerabilities. So let's look at a few of these things more in depth. So looking at where vulnerabilities may have been discovered. It's very unlikely that vulnerabilities are going to get fixed on the first try. So if there's a CVE and then they fix that, hypothetically speaking, doesn't necessarily mean that it is perfectly fixed. So most of the time, we just have programmers that just don't know how to code securely. I think there's actually a class that you can take within the program that's like literally just all about writing secure code, but it's offered through SWRE. I forget the name of the class. It's like SWRE 331, I think, something like that. Don't quote me. I'm just kind of speaking out of my butt. All right. Another thing you gotta find is like finding important to security code. So for example, it's more interesting to target a driver than kind of user space and component because drivers have access to the entire system. Sometimes programs like to sandbox components. It's a lot nicer if you can attack a part of a program that isn't sandboxed, so that way you can have full access to not only the program, maybe the system. And again, finding messy logic, things that just don't look right. If a function has a lot of if statements at the top, it's quite possible that they miss something. So like think about like whenever you're checking arguments in a main function, you're trying to see if all those arguments are in the correct format. Well, if you have a program that takes in a lot of arguments, there's a very good chance that they're going to miss that. Sometimes there's even redundant checks. This can indicate that a program doesn't actually know how to code. Again, a lot of vulnerabilities are just because of bad programmers. I guess just get good, no vulnerabilities. That's my campaign speech running 2024. No more vulnerabilities. Did I go? No? Yeah, cool. Next, you got to analyze the code. Sometimes this requires reverse engineering. Hopefully the code that you are analyzing is open source, but that's not always the case. And honestly, it's a lot more fun if you have to go reverse it. I don't know. I kind of love assembly. Again, I'm one of those masochists, by the way. I've spent my fair share of writing and looking at assembly. With that, you can kind of try and figure out what inputs you actually are able to control. So let's say you have a program there's only so much that you can actually control as a user. So things like if you're able to input, it's looking for user input and you're able to type into it, that's something you should attack. Maybe it's like it's pulling data down from your Google Drive for some reason, but you have access to that Google Drive, that's something you have control over. So look for things that you can actually directly control, and then that allows you to ultimately find vulnerabilities. This step is very important, but often overlooked. People like to just go in and just start running the program instead of actually analyzing the program. And it makes the actual finding vulnerabilities part of it very difficult because you're doing a lot of redundant things that you could have just thrown out the window if you actually just looked at the code. It's kind of like when you don't read the entire project statement when you're doing an assignment, and then you're really confused as to why something's not working, and then I come in and I'm like, oh, it's because you don't know how to read. All right, finally, we have found your vulnerability. There's two major approaches to finding your vulnerability. Manual review, this is the hardest one. Reading lots of source code, finding the common issues. But typically what we do is there's an automatic reviewers. So we have something called fuzzing, where you will have a program try to actually dynamically generate input into a function. You kind of give it some parameters to follow, and then it just goes at and just randomizes the data and just keeps pounding the binary until it breaks. Static analysis, sometimes if it's open source, you can just compile it with WAL or on GCC, and if you're on Windows, you can compile with a flag, I think it's W4. And what this will do is it will just treat all of the warnings as errors, or it won't treat all the warnings as errors. It will just generate a lot of warnings. And that means if there's a lot of warnings in the code that you're compiling, that means that the compiler acknowledges that it's bad code. And if the compiler's yelling at you, that means you've probably done something wrong. Always trust the compiler. I think I've been saying that a lot. We don't know how they work, but it's magic and it works, okay? Don't fight with the compiler because it will fight back and you will always lose. This is very time consuming. Like I said, between manual review and automatic review, I think back to that pseudo example that we were talking about earlier. They wound up using fuzzing, and I think their fuzzer ran for like 36 hours. And that's a decent portion of chunk of time. And let's say you don't get everything right in the first time and it takes 36 hours every single time. Be prepared to spend a couple weeks on something, just on one program, because you won't get it right the first time. So here's some known vulnerabilities and vulnerability classes. A lot of them are grouped into, a lot of vulnerabilities are grouped into classes. Some examples, like we kind of talked about already. You have buffer overflows. We're going to actually go through a whole example of a buffer overflow. We have integer overflow. I kind of talked about this. It's not by itself a vulnerability, but leads to other vulnerabilities because it just creates messy logic. You have uninitialized memory. So basically, if you never assigned a variable value and then you use it, there's no saying what's going to be in that variable. Memory is not always wiped, so you might just have some weird value. Printf, almost all of the standard library in C, you basically shouldn't use it. There's just vulnerabilities on vulnerabilities within the standard library, and then they just kept adding things to the standard library to make it better. Never do printf with just direct user input. That means they can do whatever they want. I don't know if you guys know how printf works, but you can put in things like %i, and then it will just, or you can put in %p, and it will just print out the pointers to everything on the stack. So that way you'll actually know what value or where your stack's actually located in memory. Other ones, like if the format specifier is %i, it will just output the data on the stack. %p is another good one. If you do %s, it's just going to treat all the data on the stack as a string, so you can actually see if there's any string data on the stack. And there's so many more vulnerabilities. Again, this is like, we only have like an hour to talk about this thing, and this probably requires an entire course. Actually, it is. I think it's 2 courses, 201 and 202. All right, so like I said, we're going to talk a lot about buffer overflows. These are very common, not as much nowadays because there's some mitigations that we'll talk about later. So a buffer overflow is caused by reading too much data into a buffer. So, little example, let's say you have an array size of 50 bytes, and then you read 100 bytes into it. What's going to happen? Who knows? Maybe your program's going to segfault, you're going to die, it's going to just die, and then that's the end of it. But not always. Sometimes it will just keep running, and then that's where it gets a lot of fun. Because you are overriding the buffer, the program will actually wind up just storing that data. If you're allocating the array on the stack, it will just store that data on the stack. So it will just, you can put almost however much data on the stack that you want, but you might overwrite other portions of the memory, and then it's just kind of just cascades down from there. Some functions that are very famous for buffer overflows. We got string copy, gets. It's a function, or I think it's gets on C. Basically, it just allows you to read from file or user input and store it into a buffer. Functions like fgets and string endcopy, even though they were made to be more secure, they also allow you to overflow. Their checks are not bulletproof. So to understand how we're going to exploit them, we need to know what we can actually overwrite. So now we're going through another example. So on the left, we have our main function. We have a buffer that's 16 bytes long. And then we use the function gets, and it will store whatever I type on the keyboard into that buffer. So if we're looking at memory right now, so we have the arguments that are passed in on the stack. We have the return address. We have the saved frame pointer, and then we have that buffer. And it looks like I have another typo. Oops. So that buffer is stored on the stack, and because it's not a pointer, it's actually going to put all 16 bytes on the stack. So that's kind of where we're starting with. Now, how do we exploit? So we know that we can overwrite the local variables because the return. Wow, that was a voice crack, jeez. Because we know the return address is also stored on the stack, we can also overwrite that. That's the fun part. And if we can overwrite the return address, we can get a shell. That is kind of complicated to explain. So basically, we can store assembly instructions on the stack, and then we can overwrite the return address to point to our assembly instructions, and those assembly instructions will be able to execute a shell or something. 15 years ago, this is how we would have done it. Doesn't really work nowadays. A lot of your systems have provided a lot of mitigation to exploiting buffer overflows with shellcode. But for ease of explanation, that's what we're going to talk about, because it's a lot easier to explain that than to actually go through what we have to do nowadays. It gets really complicated. So let's continue with our example. So again, same code on the left, but now we have been able to overwrite the buffer with more than 16 bytes of data. And if we go back, we can see this is what our original stack looked like. This is what our stack looks like now that we've been able to input shellcode. The NOPS, that stands for no operation. Basically, that means it tells the CPU to do nothing. Then we can add shellcode to that. The shellcode, again, is just assembly instructions that will allow you to execute any program really on on your PC. Typically, it's just a bash shell, so that way you're able to actually interact with the system. But it doesn't necessarily have to be a shell. Then you have your actual shellcode continued, and then you overwrite. So on that third line, that used to be the return address. Well, now we make that the address of our shellcode, so whenever the program exits, instead of returning to the previous function, it's going to return to our shellcode. Also, I have no idea what's going on in my voice right now. I'm just voice cracking left and right. This is a very bad thing. Let's say this program, I know it's a really simple program. Let's say this had root privileges. It's running as ID1. Well, if you are able to execute a shell with this program, that now means that you have a shell with root privileges. That's a big no-no. We don't like that. No shells on your system with root privileges. Please don't run just root shell on your systems. Anyways, that's just a bad idea. Don't look at me. I do that all the time, but just don't do it. So yeah, that's kind of the process of a very basic buffer overflow tag. This would be a lot easier if I could do a demo, but I think that you guys might be doing that during demo time anyways, so I'll be walking around and we can talk about that. All right, so to kind of finish this off, because we have only I think like 5 more slides, we'll talk about a little bit about return-oriented program. So in our simple method, we just made use of one stack frame, aka just one function. But like I said, you can overwrite as much as you want on the stack. So that means we can overwrite other stack frames as well. Let's say there's like 50 functions in your program. You can overwrite all of those functions data within the executable portion. So instead of just overwriting one return address, we can overwrite multiple. We're roughly just overwriting the return address of the previous stack frames, and we can work our way up the stack and do whatever we want within the system. So now we're going to talk a little bit about some mitigations. So there's this thing called ASLR. It stands for Address Space Layout Randomization. It basically randomizes the offsets of sections in memory, specifically the stack and the heap. Sometimes even the program itself. I think we talked about that vaguely earlier. Most of the time, whenever we're loading a program into memory, it starts at the same address every single time. That's not always the case. Sometimes we'll actually load the program into a different memory location. The basic idea is you can't return to something if you don't know where it is. I know it's kind of a very basic way to do something, but if you don't know where something is, there's no way you can find it. There's no way you can return to it, and that completely ruins this because previously we were basing all of our knowledge on the fact that we knew the address of our shellcode. But if we randomize where the stack location is, we won't necessarily know the address of our shellcode. So therefore, we're not going to be able to actually return to our address, and this will just segfault. Simple as that. ASLR is very important, and this was introduced, I think, the early 2000, 2005. That's why I was talking about 15 years you were able to do this, but with the introduction of ASLR, you no longer can actually do just random shellcode attacks. So there's other ones. So there's something called DEP, or Data Execution Prevention. We're able to actually mark certain portions of memory as either executable or non-executable. What we can do is we can say that the stack is not executable, so therefore if you put shellcode on the stack, it just won't execute because your CPU is going to read that. It's going to see that it's in the stack portion of memory, and then whenever you're trying to execute something, it's going to be no, and then you'll segfault again. We segfault all the time. This makes it almost impossible to execute. Actually, it makes it impossible to execute certain parts of memory. The way this is actually done through operating system lingo, we actually, it's based on a page boundary. That's a lot of just jargon that you don't need to really worry about. The only thing you need to worry about is between ASLR and data execution prevention, we have essentially broken shellcode. Shellcode attacks are almost non-existent now because it's almost impossible to write them. Doesn't mean that it is impossible. It's just very, very, very hard. And then I think the last mitigation I'm going to talk about today is something called a stack canary. This is based off of the miners back in the day. They used to walk around with canaries in the coal mines looking for natural gas. If the canary died, that means that there's natural gas, and then they were supposed to leave. We kind of do something very similar in our programs. We put a random value on the stack at the start of the function. We check to see that value has not changed. Because if it has changed, that means that we have somehow been able to overwrite it, and then the program just dies. Again, I think this causes, yet again, a segfault. And this, again, with this, it also just breaks stack overflows. It's almost some of these things are so easy to implement that it's kind of wild that they weren't implemented in the first place, but I think it just goes to show that security has not always been on people's minds, and there's a lot of very bad programmers out there. All right, I think that is the end of my presentation, and I'm finishing just on time. Would you look at that? I'll leave that open to questions if anyone has any. There's a lot of info that I talked about today.
What was that website again in the beginning that converts C into...
Oh, I'll just pull it up. It's called Compiler Explorer. Yeah, so you can kind of just look at your C code on the left. I can't actually zoom in. Oh, can I? Oh, would you look at that? Yeah, so I could write code on the left. I mean, okay, actually that doesn't work. All right, so like I can add a main function here, and I could just return like 45, and that's going to compile it, and there you go. There's my main function. Puts 45 in EAX. It's a really nice thing, especially if you're learning assembly, because you're not just going to be able to look at assembly and understand exactly what's going on. And then I can even highlight over things in the C code, and then it will show it on the right, highlighted in the assembly. Very useful program. Any other questions? All right, got another one.
Another one, yeah. So stack canaries, there's got to be. So what actually monitors the stack canary? Because wouldn't you just be able to target and defeat whatever the stack canary is using and just say, hey, everything's good, even though you're injecting shell code?
No, typically this is done through the kernel. So unless you have some way to overwrite kernel memory, no.
Okay.
It doesn't necessarily mean that it's impossible, but again, very, very, very difficult. You would basically have to find a kernel exploit at that point, and those are very hard to find. I got you. So, okay, yeah. So the question for the audience on Twitch, the question was, how is reversing used in the real world? That's kind of a very loaded question. It's used in multiple ways. It could be used with binary analysis, with like you're looking for vulnerabilities, so therefore you have to actually like do a little bit of reversing, especially in programs that aren't necessarily open source. I think a lot of the common ones, like I know people have like found vulnerabilities in Word, but Word's not necessarily open source. The thing is, though, a lot of these programs nowadays, they'll actually do in-house vulnerability research so that you will have access to the source code. Another great way that reverse engineering is used. So I do a lot of like embedded security, and finding vulnerabilities in that embedded devices, you don't necessarily have any source code. So you have to reverse everything, including the bootloader to the execution. If it's like a Raspberry Pi, typically it's running some operating system, so you have just an image file that you can just rip off and reverse that. But that's not always the case. If, like, let's say you have like an Arduino chip, that's just running the program as it is on Flash. So there's like no idea of any file format. It's literally just executing in place. That's one way that reversing is used. I don't know. There's a lot. It just depends on the use case for what you're doing. I would say most commonly it's done with exploit analysis, but that's kind of just me speaking out of my ass. That it like I don't know. I can only tell you for what I have experienced. I can't necessarily tell you what other people do with it. Any other questions? Going once, going twice. All right, so